Hi everyone, I'm Konstantina, and in this session we're going to speak about the NaiveBayes classifier. Let's start with an example of the Bayes theorem. Let's say we want to find the probability of a patient having meningitis given that they have a stiff neck. And as givens, we have that a doctor knows that meningitis causes stiff neck 50% of the time, that the prior probability of any patient having meningitis is 1 out of 50,000, and that the prior probability of any patient having a stiff neck is 1 out of 20. So, to compute the posterior probability of a patient having meningitis given that they have a stiff neck, using the Bayes rule, we are going to multiply the likelihood, which is 50%, with the prior probability of any patient having meningitis, which is 1 out of 50,000, and then divide with the prior probability of having a stiff neck, which is 1 out of 20. And as you may have guessed, we end up with a very small probability. Now, based on the Bayes theorem, we can come to a classifier that is called Bayesian classifier. And in this case, given a record with attributes A1 to AN, the goal is to predict the class C, and more specifically, we want to find the class that maximizes the probability of the class given the attributes A1 to AN. In the previous example, we had just one attribute. But can we estimate the probability of the class given various attributes directly from data? The approach of the Bayesian classifier is to compute the posterior probability of a class C, given the attributes A1 to AN, using the Bayes theorem that we saw in the previous slides. Then the classifier chooses the class that maximizes the posterior probability, or equivalently, the product of the likelihood and the prior probability of the class. But how do we estimate the probability of the attributes A1 to AN given the class C? Here comes the NaiveBayes classifier, and it is called naive because it assumes independence among attributes when a class is given, meaning that the likelihood of all attributes given the class can be estimated by computing the probability of every attribute given the class separately. Let's see an example to make things more clear. In this example, we have several information of different people. So the attributes we have are refund, marital status, taxable income, and whether they evade or not. In this case, we're interested in the last class, evade, marked in red. And we can count the probabilities of evading and not evading by just counting the cases of no and yes out of the 10 examples. We also need the probability of every attribute given the class evade, and in our case we have 3 attributes. So let's see this with an example. The probability of being married given that there is no evade is 4 out of 7. Accordingly, the probability of getting a refund given that there is evading is 0, as it does not appear in the table. But what if the data is continuous? If the data is continuous, like the taxable income in the previous example, there are several ways to deal with it. One way is to discretize, and that means putting ranges into bins. Then there is the two-way split, where you can choose only one of the 2 splits as new attribute. And finally, through probability density estimation, where we assume that the attribute follows a normal distribution. Let's see a more detailed example. Let's assume we have the previous table of attributes. We are given a test record of no refund, married with taxable income 80,000. How is NaiveBayes going to classify this new record? First, we compute all likelihoods that we need, as well as the probability of yes and the probability of no that we did in the previous slide. For the taxable income that is continuous, we find the mean and variance for each case. All these values can be seen on the left white table. So now that we have all these, we compute the probability of x given that the class evade no, which is the probability of no refund given no evade, times the probability of merit, given class no evade, times the probability of taxable income 80,000 given evade no. And accordingly, we compute the class evade yes. And since we see that the probability of X given no evade times the probability of no is larger than the probability of yes, the NaiveBayes classifies the record as no. Now, for a better understanding, you need to repeat these computations by yourselves and also try different cases of X with various incomes or other values or refund and marital status. So to summarize, the NaiveBayes classifier has several advantages, such as robustness in isolated noise points. It handles missing values by ignoring the instance during probability estimate calculations, and it is robust to irrelevant attributes. However, the major disadvantage of NaiveBayes is that the attributes are assumed to be independent, as this may not hold for all attributes. That was all for the NaiveBayes, so thank you for listening.